Assalamu alaikum. Welcome to our lecture this week. We will continue discussing the data link layer. In this lecture, we will discuss sliding window protocols and examples for data link layer protocols. All the previous protocols we have studied were simplex, where data was sent in one direction only. In real life, data need to be sent in both directions. To achieve this, we have multiple options. First, to have double links, each a simplex link in one direction, achieving a full duplex communication. Each link consists of two channels, one for data and one for acknowledgements. This means we will lose serious bandwidths for the acknowledgements. A better option is to use the same channel for both acknowledgements and data. But this will create a half duplex communication. It will save bandwidth. A better option to save more bandwidth is not to send the acknowledgements on separate frames, but rather to send them as a field in the data frames. This is what we call piggybacking. But here there is a question: for how long should the data link layer wait for the network layer to send the next packet? The answer is for a time less than the time needed for retransmission. In the following, we'll study sliding window protocols. These are data link layer protocols that provide reliable sequential delivery of data frames. The sliding window protocols are also used in transmission control protocol. These protocols allow the sending of multiple frames before receiving any acknowledgement. The sliding window refers to an imaginary box, holds frames. The sliding window is a method also known as windowing. The sliding window protocol requires sequential numbering for each frame that is sent or received. The size of the sending window determines the sequence number of the outbound frames or frames to be sent. The size of the receiving window indicates the maximum frames that the receiver can accept. The window slides at the sender side after sending a frame, at the receiver side after receiving a frame. On the sender side, here we have a window of side 3, where 3 packets are in the window. The 3 packets are sent before getting any acknowledgement. After getting acknowledgement 1, 2, and 3, the window slides to packets 4, 5, and 6. On the receiver side, this window slides after sending acknowledgements, where the last frame is acknowledged is outside of the window, and the expected frames are inside the window. The window shrinks as the frames arrived and acknowledged, and it's from its lower end, and it grows from its upper end as the frames come unacknowledged. This is an example for both sender and receiver. As you can see, the window slides as the frames be sent. It shrinks as frames be sent and slides as acknowledgements be received. On the receiver side, the window shrinks as the frames come in. It slides as the acknowledgements are sent. This is an example for 1-bit window with 3-bit sequence number, that's to say from 0 to 7. At first, there is no outstanding frame at the sender, and the receiver window indicates that it's waiting for frame 0. In the second part, the frame was sent to the receiver. At the third part, the frame was actually received by the receiver. At the fourth part, the acknowledgement was sent to the sender, and now there is no outstanding frame. The receiver is waiting for frame 1. There are three types of protocols that we're going to discuss in this lecture. 1-bit sliding window protocol, protocol using go and go back N, and a selective repeat protocol. The first protocol to examine is 1-bit sliding window protocol. In this protocol, we will use stop and wait, since the sender will wait for the acknowledgement before sending the next frame. The sequence numbers here can only be 0 or 1, since it's 1-bit only. The sending window will tell which frame to be sent, that's to say 0 or 1, and the receiving frame will tell which frames to be received, that's to say 0 and 1, or 1. As you can see here, the sender will send a frame, the receiver will send an acknowledgement, another frame will be sent, another acknowledgement will be sent, and so forth. Let us examine a different scenario, where A is trying to send frame 0 to B, and B is trying to send its frame 0 to A. Suppose that A has sent its frame to B, but A has a very short timer where it times out before the acknowledgement sent back from B. That means A will send series of identical frames, all with sequence number 0 and acknowledgement 1. When the first frame reaches B, it will be accepted. All the subsequent frames will be rejected because B is waiting for frame 1, not 0. Furthermore, all the duplicates have acknowledgement 1 and B is still waiting for acknowledgement 0. B will not get its next frame until one of the acknowledgements reaches A, causing A to get its next frame and send it to B with the right acknowledgement. The protocol will be in a loop. Another particular situation arises when both sides simultaneously send initial frames. If both A and B send initial frames to each other and they crossed, this will cause multiple frames to be resent, and although there is no transmission errors. In fact, half of the frames will be duplicates. This can happen also with premature timeouts. But even if miscommunication occurred and frames and acknowledgements went missing or duplicated, no compilation of lost frames or premature timeouts can cause the protocol to deliver duplicate frames or packets and to skip a packet or to go into a deadlock. It might go into a long loop, but no deadlocks. In situations like long-distance communication, such as satellite communication, there will be a long round trip. That's to say, the data takes a long time to reach the receiver, and the acknowledgement takes as long to reach the sender. As an example, let us examine 50 kilobytes per second satellite channel with 500 milliseconds round trip. At time 0, the sender will start sending the frame. At time 20, the whole frame is already sent. Not until time 270, the frame will not fully reach at the receiver. Not until time 520, the acknowledgement will arrive back at the sender. Under the best circumstances, where there is no waiting at the receiver and the acknowledgement itself is short, the sender will be blocked for 500 milliseconds out of 520 milliseconds for 96% of the time. In other words, only 4% of the bandwidth is used. The solution here is to allow the sender to transmit multiple frames before blocking itself instead of just one frame. With a large enough choice of number of frames that can be sent, the sender will be able continuously to transmit frames since acknowledgement will arrive for the previous frames before the window becomes full. This technique is called pipelining. With pipelining, some questions arise. What happened if a frame in the middle of a long stream was damaged or lost? and what the receiver should do with all consequent frames that follow it. There are two basic approaches that we will discuss. The first approach is go back and automatic repeat request protocol that provides sending multiple frames before receiving acknowledgement for the first frame. The frames are, of course, sequentially numbered, and the frames are sent in order. If the acknowledgement for any frame was not received within the time period, all frames starting from that frame will be retransmitted. This approach can waste a lot of bandwidth if the error rate was high. For example, here, frame 1 has reached without error, frame 2 was errorless and discarded. When frame 3 reached the destination, it was also discarded. When frame 4 has reached the destination, it was also discarded. Then the sender has timed out, recognizing that there is no acknowledgement but only for frame 1. So it will start sending from frame 2, 3, and 4. It won't send any other frames until it gets the acknowledgements. Here an example for frame 2 where the frame 2 is an error, and all the subsequent frames will be discarded until frame 2 is resent and reach the destination safely. Then the sender will resend all the subsequent frames and frames will be delivered in order. This protocol allows sending multiple frames as we see, but as we have said also, it wastes bandwidth. The other option is selective repeat, automatic repeat request. This protocol also provides the sender to send multiple frames before receiving acknowledgements. However, only the errorless frames here are retransmitted, which means there should be a way for the receiver to buffer the good frames that were sent after the errorless frame. Selective repeat often combined with what we call negative acknowledgement. This is where the receiver sends negative acknowledgement upon arrival of a damaged frame. This approach requires a large amount of data link layer memory if the window size was large. As we see here, when frame 2 was an error, all the subsequent frames were reserved, were buffered, until frame 2 was received, and then they will be processed. That means the network layer will receive the packets in the same order they were sent. Note that the reliable data communication is also a requirement for transport layer. So, will TCP use GPN or CRSR? Actually, TCP uses GPN with buffers to improve the performance of the pure GPN. As we have said already, the two alternatives are trade-offs between efficient bandwidth and buffer space, depending on which resource is available. Then you can pick which protocol you're going to use. See you in the next part.